Have you ever considered the importance of protein? When you think of protein, your first thought might be to the dietary role of proteins, things like beef or beans or chicken, and the importance that they have to our everyday diets. Or you might think of muscles and the protein in our muscles that we use to move our body and to accomplish our daily activities. Of course, the importance of proteins actually extends far beyond these two examples. Proteins act as catalysts in nearly every biological process that occurs within our bodies. Without proteins, we wouldn't function. Now, all those proteins require one simple organic functional group, our amides. Amides, of course, aren't the only organic functional group found in proteins, but they do make up the core backbone, we'd say, of our proteins that link small organic molecules together to make those large protein structures that make all of our daily activities possible. Our amide, of course, consists of a carbonyl, our carbon with that double bond to oxygen, bonded to a nitrogen that can then be bonded to either carbons or hydrogens depending on the structure. So of course it's another example of one of our carboxylic acid derivatives where we still have that carbonyl bonded to our electronegative nitrogen in this case. Now, one of the things that's unique to our amides is that we can actually have multiple different kinds of amides based on the number of carbon bonds to our nitrogen. Or in other words, the substitution pattern of our amides can vary. For our previous carboxylic acid derivatives, such as our acid chloride, right, that chlorine only had one bond, which would always be to our carbonyl carbon, and so there's no possible change in the substitution state of that chlorine. Even with our oxygens, right, with our ester, our oxygen always wants two bonds, one to its carbon chain, and then one to the carbonyl oxygen. Here with our amides, our nitrogen can accommodate three bonds. One of those bonds is always going to be to our carbonyl carbon again, but we could have two bonds to hydrogens. So this would be somewhat like our carboxylic acid, in the sense that our electronegative atom is only bonded to other hydrogens in addition to the carbonyl carbon. Or we could have our nitrogen bonded to one carbon chain. So I'll represent that as an R over here. Or we could have that nitrogen bonded to two different carbon chains in addition to our carbonyl carbon. Now what we see here is three different substitution states for our nitrogen. So in this case, with only one carbon to our nitrogen of our amide, we refer to this as a primary amide. Here we have a secondary amide with our nitrogen attached to two different carbons. And of course, our final state is a tertiary amide, where our nitrogen is connected to three different carbons, right? Our carbonyl carbon and then two different carbon chains. The substitution state of our amide will actually influence how our amide behaves. So as we look at our physical properties of our different amides, of course all of these will have dipole-dipole interactions, right? Our nitrogen is always electronegative and our oxygen is always electronegative. So we're always going to have these dipoles here away from our carbonyl carbon and out to our electronegative atoms. But what's unique as we change that substitution pattern is our hydrogen bonding within our amides. So for our primary amide, notice we have our two different possibilities here for hydrogen bond donors. Right? We have two hydrogens bonded onto our nitrogen that can act as hydrogen bond donors. With our secondary amide, we have one hydrogen bond donor with that single hydrogen bonded to our nitrogen. With our tertiary amide, we have no hydrogen bond donors. Right? So our oxygen and our nitrogen here can both accept hydrogen bonds from things like water, but they can't form them by themselves. Right? So if we have a tertiary amide, we're not going to have any hydrogen bonding, and so it will tend to have low boiling points and melting points compared to our secondary or our primary amides. So this would be more comparable to like an ester, right? Where again with esters, we don't have any hydrogen bond donors. We do have dipole-dipole interactions, and so we have moderate to low melting points and boiling points. However, as we look at our secondary and our primary amides, here we do have those hydrogen bond donors, which means we're going to have hydrogen bonding between our secondary amides as well as between our primary amides. And so here we'll have much higher melting points and boiling points as we add in those stronger intermolecular interactions. Of course, as always, that also corresponds with higher water solubility. So our primary and secondary amides essentially behave a little bit more like carboxylic acids in terms of their solubility, melting points and boiling points, whereas our tertiary amides will behave much more like esters in terms of that solubility and their melting points and boiling points. Now let's consider the reactivity of our amides. Like all of our carboxylic acid derivatives, our amides can undergo nucleophilic acyl substitution reactions. However, as we saw when we looked at our nucleophilic acyl substitution mechanism, our amides are the least reactive of all of our carboxylic acid derivatives. This is in large part due to the strong resonance that we have in our amides, right? So our nitrogen is somewhat less electronegative, so it's willing to donate its electrons in towards our carbon and then ultimately towards our oxygen. And so this means that we have a significant resonance contributor here where our nitrogen is double bonded to our carbon and our oxygen is taking that negative charge. Right? So this carbon-nitrogen bond actually has somewhat of a partial double bond characteristic. And of course this also means that our nitrogen here isn't a particularly great leaving group. So we tend to be somewhat more stable here in our amide structure, and while we can do some nucleophilic acyl substitution reactions, we're much less reactive compared to our other carboxylic acid derivatives. So we still can see things like hydrolysis reactions or converting to other carboxylic acid derivatives. It's just somewhat harder with our amides. Again, I'll just quickly show what that hydrolysis would look like. So we could have an amide reacting in either basic or acidic conditions and being hydrolyzed to a carboxylic acid. Let's say we have basic conditions here. So we're bringing in a strong base. So this could be sodium hydroxide. We do our usual attack to form our tetrahedral intermediate. And then, as usual, we can bring our electrons back down and kick off our leaving group. So this would be the elimination step that we typically see in our nucleophilic acyl substitution reactions. And we kick off our nitrogen-based leaving group. This is going to be negatively charged. Now our nitrogen here is a much stronger base, and our oxygen, of course, here in our carboxylic acid is a weak acid. So this will actually react further and be deprotonated to our carboxylate. So this would then come down to our carboxylate of our negatively charged carboxylic acid, and we would form an amine from our nitrogen here. So we can perform this hydrolysis again, as I mentioned, with both basic and acidic conditions. The reaction would look very similar in acidic conditions. but in that case, we would end up with our protonated carboxylic acid instead of our carboxylate here. So our nitrogen would actually break off with a hydrogen. We'd be protonating it before that breaks off, and then we just end up with our amine and our carboxylic acid. Now, while our amide itself is not particularly reactive, we can use it to create our nitrile functional group, which then has some interesting reactivity. Our nitriles can form through a dehydration reaction with our amide. So if we start with our amide, we have our carbon with our nitrogen attached. This works for only our primary amides. So we have our two hydrogens and our carbonyl carbon there. And then we're going to react, and we're going to be eliminating water. So water is coming out as one of our products. It's a dehydration, right? Dehydration always implies eliminating water. That's taking our oxygen up here and our two hydrogens on our nitrogen to create our nitrile. Now, this sort of dehydration reaction, of course, requires that our oxygen break off as a leaving group. So we need something to convert that oxygen into a good leaving group. Often, this phosphorus-based compound is used. And then, of course, we include heat as well. Heat is commonly used in dehydration reactions to help eliminate that water as we go to produce our nitrile product. So, for example, we might have, say, our butanamide here. Again, of course, we can't have any carbons on here attached to our nitrogen because we're going to end up with all three of our nitrogen bonds to our carbon at the end of our reaction here. Again, I'd be adding my phosphorus compound with heat. And I'm just removing my oxygen and my two hydrogens, H2O, and then I get my same carbon skeleton, but then with the triple bond to my nitrogen instead of that single bond to my nitrogen and the double bond to my oxygen. So I still have my four carbons, but now my nitrogen here with the triple bond instead of my amide functional group. Following my dehydration reaction with my amides, I've now created a new function group of my nitrile. Now, we have seen nitriles in a few places before, right? So we saw that we could form nitriles through addition of cyanide to our carbonyls, our ketones, or our aldehydes. We also saw that our cyanide ion, the carbon and the nitrogen there, could act as a pretty good nucleophile, so we could form nitriles through substitution reactions with alkyl halides. And I do want to talk a little bit more about nitriles here because they have some interesting reactivity themselves. Of course, our carbon and nitrogen has a polarized bond where our nitrogen, of course, is more electronegative. It's going to be pulling those electrons toward itself. And our carbon then becomes partial positive. And so our carbon is electrophilic here, similar to our carbonyl carbon in a ketone or an aldehyde. So they actually will behave somewhat like our ketones and aldehydes, just that they have a nitrogen instead of an oxygen. Now, our carbon here isn't as electrophilic as a ketone or an aldehyde. So our nitriles are somewhat less reactive than our ketones and aldehydes, but they do see some similar reactions. Let's start with hydrolysis. As we saw with ketones and aldehydes, if you add water to a carbonyl, that water can attack that electrophilic carbonyl carbon, resulting in, for our aldehydes and our ketones, the creation of a diol. Right? You'd end up with two oxygens attached to that electrophilic carbon. Now, if we do that here for our nitrile, so we're still going to have that water attacking our electrophilic carbon, but interestingly, it's actually going to end up leading to an amide here instead. So this can occur with either base or acid. And we'll create an amide initially. Now, of course, you should remember from our previous discussion, right, that our amide itself can also react in a hydrolysis reaction. So under those same conditions, our amide is going to continue on to our carboxylic acid. So when we hydrolyze our nitrile, we usually go straight through our amide and end up at a carboxylic acid. As I mentioned, our mechanism here is based on our nucleophilic water, or hydroxide in the case of basic conditions, attacking that electrophilic carbon of our nitrile. So we attack there, and we move our electrons out of the way to make room for our new bonds. This gives us our hydroxy group attached to that electrophilic carbon, and now just a double bond to our nitrogen. Now this is negatively charged, so we're going to take the hydrogen from our water in solution. And you should notice here, we're starting to look quite similar to our amide, but it's the resonance structure of our amide where our nitrogen has the double bond. So all we have to do here is a proton exchange. So we're going to have a base come in and take off this hydrogen. Since we're doing this under basic conditions, pull that off. That will make our oxygen negatively charged. And so then we'll bring our electrons down to make the double bond and pull another proton from our water in order to get our second proton on our amide here. And again, as I showed you earlier, right, that hydrolysis would continue all the way to our carboxylic acid. Following that mechanism for our amide hydrolysis, that it uses our usual nucleophilic acyl substitution, addition, elimination mechanism. Again, as I mentioned, we can also do this under acidic conditions. That will follow the same basic mechanism. We would just be protonating before we complete our nucleophilic attack steps to help with our various leaving groups here. Now, one of the other common addition reactions that we saw with our carbonyls is our organometallic addition. So if we take an organometallic compound, so that would be our carbon chain connected to some metal, whether it's lithium or our magnesium in our Grignard reagents, we would react that with our nitrile here in this case, and again, this is going to act as a nucleophile. Our nucleophilic carbon in that organometallic bond will attack our carbon, and this ends up adding on to create an imine. So we have our extra carbon chain added on, and a double bond to our nitrogen. As usual, of course, this would occur using our anhydrous conditions in the first step, followed by acid to protonate our nitrogen to make that final imine here. Imine you might recognize because we saw it when we added amines to our aldehydes and ketones in a nucleophilic addition reaction there. And one of the things that we see with imines, right, is under acidic conditions, that will actually get pushed back towards an aldehyde or a ketone. So since we have acid, of course, here in our second step of our reaction, we actually won't stop at our imine, but this will continue to react to create our ketone. So our acid ends up attacking again, and we replace our nitrogen here with our oxygen. Again, the mechanism here is going to be very reminiscent of the reactions that we saw with our carbonyls. Right? We use the electrons of our nucleophilic bond between our metal and our carbon to attack that electrophilic carbon of our nitrile. We move our electrons out of the way. This gives us our imine here with our double bond to nitrogen and our new carbon chain, in this case just 2 carbons added on here at the end. This, of course, gets protonated by our acid that we add in the second step. Leading to our initial imine product. With the extra carbon chain. And then this imine product will react following the same mechanism that we looked at previously. It's just the reversal of the nitrogen addition to our ketone. And we create our ketone form. So we got our oxygen there, and again, the 2 additional carbons that we added on with our ethyl lithium compound here. So again, the reactions are quite similar to our carbonyls. The difference is just that we're actually slightly less electrophilic here at our carbon, since we have the less electronegative nitrogen compared to our highly electronegative oxygen. And so then that slightly changes up what our reaction looks like. Right? Instead of getting alcohol, we get that imine that then reacts to get our ketone. Or of course, in the case of our hydrolysis reaction, or our hydration reaction, we add on our water in order to create our amide, which then is further hydrolyzed to our carboxylic acid. So here we've seen 2 different examples of nitrogen-based functional groups that, of course, either are carboxylic acid derivatives, in the case of our amide, or have a lot of similarities to our carbonyls, in the case of our nitrile. Now, the amides themselves tend to be relatively unreactive, and this is actually very important biologically, right? Our proteins need to be relatively stable so that they can continue to carry out those biological functions. We don't want those amide bonds kind of falling apart, leading to our proteins falling apart. However, amides do still have some interesting roles in organic synthesis because we can use them to create things like nitriles that then allow for other interesting reaction possibilities.